Okay, day 29, integration by substitution, will be spread out over 2 days. This is the first day. The first screen has a lot of notation, and I think it's better just to jump quickly to examples. When we take derivatives, we have the chain rule. You take the derivative of the outer function, capital F, to get F prime, but then you go to the inner function, G, and take the derivative of that, G prime, the chain rule. We now also have a way of taking the antiderivative of two functions that are set up in a situation that looks like the chain rule so that we get what we started with over here. It's kind of hard to see this with the notation, but realize that the antidifferentiation of a composite function is possible. All right, there's 3 examples on this page. I'm going to do the first one in detail, and then I'm going to help you get started on the second and third, and you're going to finish on your own. So when I look at the first one, I see 2 functions. I see x to the third, and I see the square root of x to the fourth plus fifth. And since I see 2 functions, I'd like to have something that looks like the product or the end result of a chain rule. If I take the derivative of x to the fourth, I would get 4x to the third, which is kind of what's sitting here. I'm missing the 4, but I can take care of that in a minute. But if I take the derivative of x to the fourth plus 5, I again get 4x to the third. So my hint is that this is the chain rule result, and this is the original function. So down here I'm going to highlight and say x to the fourth plus 5 is going to be my u function. I'm going to replace that with u. I'm going to leave the square root alone because that has nothing to do with the derivative function, which is x to the third. The derivative of u is now 4x to the third dx, and a lot of that stuff appears in the original question. Dx is there, and x to the third is there. I need to throw in an extra 4 right here. That's in the wrong color. I'm going to change colors for that. I need to throw in a 4 so that the du is there in its entirety. I need 4x to the third dx. dx is there, x to the third is there, I need a 4. But I can't just add a 4 to a problem, so to offset that 4, I put another 1/4 outside so that the result of 1/4 times 4 is 1. The one on the outside is going to stay there, 1/4, but now the inside collapses into a much shorter problem. 4x to the third and dx are all part of du. U is x to the fourth plus 5, and the square root is u to the 1/2. We know how to do this. The antiderivative of u to the 1/2 is increase the exponent by 1, so that becomes 3/2. Take the reciprocal, 2/3, 1/4, 2/3 times u to the 3/2 plus c. Then I go back and I change u into x to the fourth plus 5, and that works. And if you want to check it, we're going to take the derivative of this now to make sure that we did it correctly. 1/6, bring down the exponent, 3/2. X to the fourth plus 5, reduce your exponent by 1, that becomes 1/2. Chain rule, the derivative of the inside part is 4x to the third, and then plus the derivative of c is 0. If you simplify all that, it's going to match exactly what we started with up there. 1/6 times 3/2 is 1/4, but 1/4 times the 4 that's sitting here is 1, so those go away. X to the fourth plus 5 to the 1/2 is the square root of x to the fourth plus 5, and I've got x cubed left over, which is going to be moved to the front. So, second example, I've got it set up and highlighted. It looks like x to the third is 1 degree bigger than x squared, so I'm going to let u equal x to the third, and I'm going to take the derivative of that and see if it works out nice and neat. So again, in blue, I've got u equals x to the third. In green, I'll do du. du is 3x squared dx. And now if I look, dx is taken care of, 3x squared is taken care of, I have x to the third taken care of. So my new question is, what is the antiderivative of cosine u du? Okay, that one's not so hard to do. The antiderivative of cosine, the derivative of cosine is a negative sign, but the antiderivative is the other direction. So the antiderivative of cosine is sine u plus c. I'm going to go back and replace that u with my substitution. U is the same thing as x cubed, so my final answer is sine x cubed plus c. And again, if you check and take the derivative of that, you wind up with what you started with, 3x squared cosine x cubed. The derivative of sine is cosine, so I get cosine x cubed, but then by the chain rule, I need to take the derivative of x cubed and get 3x squared. Okay, last one. Once again, when I look at these things, I see sine and cosine. The cosine has an exponent, so that's a good case for just leaving that stuff there. I'm going to turn that into a u, which means This is going to be the du part, okay? And notice, I'm not worrying about the cube part yet. I can take the antiderivative of u cubed or something to the third power. What I'm concerned with is the chain rule. The derivative of cosine is negative sine. I can deal with the negative and that's fine. So there's a hint. I'm going to suggest that you pause the video, try and figure out what u and du are. So write down what you think u should be, write down what du should be, and then set up your antiderivative statement. Okay, let's see if we can figure this one out. If we let u equal cosine 2x, then du is equal to, the derivative of cosine is negative sine, and then by the chain rule, I've got the derivative of 2x, which is 2, so du is negative 2 sine 2x dx, okay? Next step is to see if we've accounted for everything that appeared in the original statement. U is cosine 2x, so I'm going to need to not write with a highlighter. So I'm going to need u cubed, and then I need to have a negative 2 sine 2x dx. Sine 2x dx is all there. What I'm missing is the negative 2. So I'm going to put a negative 2 inside the problem. I'm going to put it right here, and then to offset that negative 2, I need a negative 1/2 on the outside. The stuff that's in red will cancel out. So now what I've got is, I've got 2x dx negative 2, sine 2x dx negative 2, so that's all the du stuff. So what you're doing is you're taking the original problem and just splitting it into different chunks that are accounted for with either the u or the du. So once again, this is a much easier problem to do. Bring down your negative 1/2 because that did not disappear inside the du statement. So now I've got negative 1/2 times the antiderivative of u to the third du. Pretty straightforward. 1/4 u to the fourth plus c. Multiplying out, negative 1/8 u plus c, and I'm going to change the u back into cosine 2x plus c. So final answer is right there. If you take the derivative of that, you'll find out that you'll wind up with exactly what you started with. Take the derivative of that and you're going to wind up with cosine cubed 2x. Oh, I'm missing to the fourth. That's why it doesn't make any sense. It's u to the fourth. Now it's good. So in the third of the 4 slides for today, we've got a slope field and a differential equation, and we're supposed to solve the differential equation to come up with the answer of y equals. Part A says sketch 2 approximate solutions of the differential equation, one of which passes through the given point. So when I look at what's happening in the slope field, left of negative 1, slopes are going up. Right of negative 1, slopes are going down. Left of 1, slopes are going up. And right of 1, slopes are going down. So what I'm going to do is draw some sort of a curve that seems to peak at negative 1, comes down, peaks at positive 1, comes down again. Something like that. I don't like the way that that's drawn, so let's try that again. 1, down, up, and down again. So something like that. And since you're supposed to draw 2, I could start pretty much anywhere and have that pattern. Peaks at negative 1, comes down, peaks at 1, comes down. Something like that. Okay, you can see the solution on the right. And again, we're working with u substitutions, so let's break this apart. You're going to bring the dx up to the other side. So now I've got dy equals that big long function dx. We're going to take the antiderivative of both sides so that the antiderivative of dy is y, and the antiderivative of all this stuff we need to figure out. So again, I'm going to look at my exponents. 1 minus x squared. If I take the derivative of x squared, I wind up with x to the first, which I have sitting here. We don't have to worry about constants yet. You can move a constant out front. That's the first thing I did. So I let u equal 1 minus x squared. After I take u as 1 minus x squared, du is a negative 2x dx. So I have a dx, I have an x, but what I need to include is a new negative 2. So right here, you can see that I threw in a negative 2, and now I offset it with a negative 1/2. So now the original question with this new negative 1/2 and negative 2 is set up perfectly for a u substitution. Blue stuff is u to the 1/3. Green stuff with the -2 is du, so that's du. And then on the outside I have 5 times -1/2, which is -5/2. Antiderivative u to the 1/3 is 3/4 u to the 4/3. Okay, I'm going to change that u back into what I substituted. U is 1 minus x squared. I have -15ths. And then if I need to find out the constant, and I'm choosing 1, 1 because I was told that I had to have one solution, I went to the point 1, 1. When I plug in 1, 1, I wind up with c equals 1. So my final solution is this. And if you type that into decimals, you'll see a function that looks a lot like this. Okay, final slide for day 1, and I realize it says day 2 here, but there's a lot to do on day 2, so I'm going to throw this into day 1. Sometimes u substitutions aren't quite enough and you need to do an extra step, which is called change of variable. And this can happen in 2 cases, both of which you'll see here. Case number 1 is when you have a definite integral. Okay, a and b are values for x, but if I do a u substitution, I'm going to need to take a and b and also plug them into the new function that's created when I set up my u substitution. So that's part 1. Part 2 you'll see down here. If I look at my functions here, 4x plus 1 is inside of 1/2, so that's a good candidate for u. I'm going to let u equal 4x plus 1. But taking the derivative of 4x plus 1 leaves me with 4 dx. Now the 4 doesn't bother me and the dx is okay, but what's missing is I haven't taken care of this x yet. So I'm going to kind of plow ahead and just worry about getting rid of this x in a second. So I've got this, which is going to be my u. I've got dx, and I put a 4 here so that I have a du. Du is 4 dx. Those two are taken care of. I've got 1/4 on the outside to offset the 4 that I created so that I would have 4 dx. But now I still have this x. And the other issue is that when I change everything to u's, 0 and 2 for x are going to be no good. So the change of variable step says this. Look at your u substitution and say that I need this x to disappear. So I'm going to take my u and solve it for x. X equals u minus 1 over 4. Okay? So I'm going to replace this red x with u minus 1 over 4 in a second. But at the same time, I also know that if I plug in 0, the lower limit for my bound, into here, I know that's the same thing as getting u equals 1. And if I plug 2, the lower limit for my bound, into the u substitution, I get u is 9. So now that tells me that when I set up my antiderivative for dx going between 0 and 2, that's the same thing as having du going between 1 and 9. So the result is over here. 1/4 came from offsetting the 4 that I had to put in to make a 4 dx. 1 to 9 is because now I'm taking the antiderivative with respect to u. U to the 1/2 was my original u substitution, and u minus 1 over 4 was the way I got rid of x. Now everything is in terms of u's, and I can do a little bit of simplifying, and this isn't so bad. 1/4 comes outside, 1/16. I've got u minus 1 times u to the 1/2. This u to the 1/2 can get distributed to both of these terms. Add your exponents. 1 plus 1/2 is 3/2. U to the 1/2 times 1 is u to the 1/2. Now the antiderivative of these is just using your power rule. The antiderivative of u to the 3/2 is add 1 becomes 5/2. Reciprocal is 2/5. 2/5 u to the 5/2. Add 1, reciprocate, 2/3 u to the 3/2. I'm going to go between 1 and 9 for my u's. And then when I get my results, I'm going to multiply by 1/16. So once you get to this point here, the antiderivative is just plowing through a bunch of calculations with fractions and exponents. So plugging in 9, the square root of 9 is 3, so I have 3 to the 5th. Square root of 9 is 3, so I have 3 to the 3rd. That's why I have 3 to the 5th and 3 to the 3rd here. Plugging in 1, those collapse down to nice, neat numbers. Grind through all this information, and you wind up with a final answer of 149 over 30. Okay, so don't be intimidated by u substitutions. The more you do them, the easier they get. And you'll have plenty of practice with u substitutions.